So thanks a lot. Thanks to the organizers for the opportunity. It's great to be at least virtually here. Okay, so what I'm going to discuss today is a joint project with Laurent Gruson and Nicolas. Okay, and I will be working over C. Okay, over field of complex numbers. All right, so let me start with some motivation. Okay, so say like how I got interested in this notion of rational simple connectedness, which is, I mean, from my perspective, it comes from birational classification of algebraic varieties and minimal model program. So just put this thing. Can I just close it? Yes, great. And MMP. Okay. All right, so let me recall something which people know, but I mean, just to start with. So if you start with Z smooth projective variety, and say with Codera dimension minus infinity, okay, then if you believe in all the conjectures of minimal model program, so let me say MMP conjecture, I mean, actually here is abundance, but anyway, like all the conjectures in the minimal model program world, then Z should be birational to a Mori fiber space. Okay, so we have seen this in several talks. Like, let me just fix a little bit of notation. So I will write it pi W over B, which is a Fano vibration minimal, which is minimal in like in the sense of pk rank. So like this is a Fano vibration, huh? Okay. All right. So these are Fano vibrations. So in particular, look at the general fiber. And this guy is going to be rationally connected. Right. So this is, well, of course, I mean, this is classical now. This is Campana, Collarmia Okamori. Okay, then singular cases, other contributions. Okay, so right, so we have this Fano vibration, and the question is, I can ask, say, I reduce myself to the study of this kind of Fano vibrations, and I can ask some structural questions on the on this Fano vibration. So the question I will ask, so does pi admit a rational section? Okay, this is like a natural question you ask when you have a vibration. All right. If you prefer, like more algebraically, you can just take you can take the generic fiber of this vibration. You can look at his CB point, this is the rational function over the base, and you ask if this guy is non-empty. Okay. All right, and so there is a classical result, okay, which answers this question if the base of this vibration is a curve. And also this is like a very classical result. This is Graber, Harris, and Starr. This is in, okay, So the result implies that if B is a curve, then pi has a section. Okay, in a sense, the answer, okay, is yes, and this has been known for some time now. And so, of course, if you're interested in arbitrary fibrations, of course, when you run like the MMP, you can end up with other bases, of course, of higher dimension. So let me stress that if B is not a curve, so is, for instance, a smooth surface, then there are many Fano fibrations with no rational section. Okay. Well, an example which comes to mind immediately are conic bundles. We have seen this these days, like several examples. Let me just, I mean, to fix ideas, let me just write down an explicit example here. Okay, I like this color thing. I mean, for this, hopefully I won't be too much. Okay, try to find. Okay, so take, this is just an example. Take P2 cross P2. Take inside here. Let me just really write equations. Okay, that is up. Okay, so this guy is W. Okay, and then you fiber over P2, where the P2 is the one with coordinates. Okay, here is like the xi coordinate. Okay, and so this is a conic bundle. And what is the picture of this? Well, you have your P2 downstairs, vibration here. So here up your W. Okay, and then you have downstairs your okay, like the 3 coordinate lines. Okay, and then so if you take a guy outside, then you get the fiber is like a smooth conic like this. If you take general point on one of those lines, then you get a double line. Okay, and of course, if you go on the intersection of the coordinate lines, then you get a double line. Okay, you can check this is like by hand. I mean, really by hand in this case. This is as no rational section, so pi has no rational section. Okay, so my point is that it's easy to produce examples of Mori fiber spaces without rational sections. Okay, over surfaces, even over P2 here is the case. It's very easy. Okay, so the problem one can try to attack. So problem is how to generalize to get some positive results and to generalize so Graeber, Harris, and Starr in dimension 2, for instance. So generalize Graeber, Harris, and Starr when B is a smooth surface, for instance. Okay. Okay, so let's try to get some intuition about what's going on here. So let me recall a well-known classical result. And so if you want a special case, okay. So a classical result in this direction, it's an Lang theorem. Okay, so this is well, I mean, So I will be vague about the dates, but it should be like in the 30s and the 50s, like the generalization. Anyway, what does he say? He says that if you take the function field where, I mean, B's are dimensional, and take xd inside Pn, okay, a degree d hypersurface over K, such that, so you want a numerical condition, which is this on the degree, so such that d power r is less or equal than n is the dimension of the projective space. Then this guy has rational points. So K is not okay. So you see, this is some kind of sufficient condition which tells you, guarantees that you can get rational points. Okay, and this is the case, of special case, of course, it's the case of Fano hypersurfaces, but still is a very interesting result in this direction. So let me, I want to stress like some special cases of this. Yeah, just avoid to use too many colors. Okay, so look at the case r equal 1. Okay, this is just so this condition, this is exactly the same as being Fano. Okay, so this is equivalent to be right here, Fano. So x, of course, I'm taking, or maybe I should say like taking a hypersurface here, huh? A smooth hypersurface. Okay. And this is the same, so you can describe this geometrically, as we said, via the rational connectedness. Okay. So the question is, okay, what happens in dimension, sorry, yeah, like for r equal 2. Okay. So you have this numerical condition. Okay. This clearly implies Fano. Okay, this is strictly stronger than being Fano. And the question is, okay, can we describe geometrically in terms of rational curves this numerical condition, d square less or equal than n? So I would like to find some kind of nice geometric condition here. Okay, like to replace rational connectedness, okay, which should be equivalent to this numerical condition, d square less or equal than n. Okay, and here is where the idea comes, okay, this kind of topological intuition. Okay, so the idea, as far as I know, this is to Berry-Mazur. And let me also mention the Jong and Starr. He will appear like several times today, okay, in this talk. So this guy here should be an algebraic analog of simple connectedness in topology. All right, so how they come up with this idea? Okay, well, this is like inspired by topology. So especially when you look at topological fibrations over two-dimensional CW complex. Okay, I don't want to spend like time on this, but let me try to see how you get to the definition which I will describe of rationally simply connectedness, which is this notion. Okay, so start from topology. Okay. Okay. So let me recall like one way to describe, to define simple connectedness in topology. So a topological space is simply connected you can see it this way. So if you look at the space of two base paths, you want this guy to be path connected. So if the space of two base paths is path connected, okay. So let me. So what happens if you want an algebraic analog? So basically, you want to replace all the all the paths here with rational curves. Okay, and this is basically the intuition on the definition of rationally simple connectedness. Rational simple connectedness. So in algebraic geometry, so algebraic variety, I will say that is rationally simply connected. Okay, here you have this space of two base paths. What is the space you should consider? As I said, you replace path with rational curves. So here you just replace this guy with moduli space of rational curves. Okay, and what do you ask? Well, you ask rational connectedness of this guy. Okay. All right, so this is just the first idea, okay? I didn't give you like a very precise definition, okay? But this is just to how you get this notion, okay? That was my goal, okay? All right, so let me just, before getting more rigorous and giving you like an actual definition of rationally simply connected variety, I want to make a comment, okay? Maybe I leave it like this. Let me make a comment here. I shouldn't write like that. You see, this is just one possible generalization of the numerical condition d square less or equal than n, but there are others. So let me, I stress this because maybe one could be tempted to say that this is exactly the same, but it's not. Okay, so other possible ways, I will mention one to generalize the numerical condition to Fano variety. So this condition here, okay. So you see, for hypersurfaces, this condition star is equivalent to asking the second term character of x to be positive. Okay, this is just a computation, and you see, one could say, okay, no, well, the way I like to generalize this condition is just to ask for a Fano variety to verify this positivity of the second term character. And for this, there is a name for this. So variety is verifying this. So Fano with a second term character positive. are called two Fano. Okay. In a sense, in principle, at least this condition should be easier to check. Okay, with respect to this notion on the moduli spaces of rational curves. Okay. All right. And of course, there is a lot of literature also on this. So understanding which Fano varieties are two Fanos. Okay. All right. So let me now be more rigorous and define you, give you a definition of rationally simply connected. Okay. All right. So let me fix some notation. So I take X, smooth, projective variety. And let me assume that the Picard rank of X is 1. Okay. This is so how to say, this simplifies the definition, okay? But in principle, you can give other definitions for arbitrary varieties, okay? But here I will assume this for today's talk. Okay, take so I take the moduli space, because of course there are many moduli spaces, right? So you fix a degree with respect to the generator of the Picard, and take so this guy, so which moduli space of degree D stable rational curve with unmarked points. Okay, so you take this guy, and this comes with an evaluation map. Okay, so evaluation M0 and bar X D. Okay. What is the remark? Is that remark for M equal 2? Okay, look at the fibers of F2, if you want, are exactly the analog of two-based paths for topological spaces. So the fibers of F2 are the algebraic analog of two-based paths in topology. So this is the space we are interested in, okay? And right, so, and now I can give you the definition, finally. Okay. Okay. All right, so I say that X is, okay, let me make some rationally simply connected. Okay, if, what do you ask? So you fix a degree, so there exists a D naught 0 such that for all D bigger or equal than D naught, so you fix a degree and you look at the moduli spaces of high enough degree, okay? And what you ask is that, so for every D there exists M, let me D2, okay, canonical component of this moduli space here. So 0M, but let me explain X D. Okay, so is this guy. So this is the moduli space. I mean, so the moduli space parameterizing the morphism which are birational onto the image. Okay, and so there is this irreducible component. Okay, such that you look at the evaluation from MD2 over X2. You look at the fiber, you ask this guy to be dominant. Dominant. And you ask the general fiber is rationally connected. Okay. Here we are. Okay. So let me write this. Okay. So I should mention, so the first so this definition, let's say there are several different definitions, but let's say the first one is certainly due to the Jong and Starr, who came up with a rigorous definition of rationally simply connectedness. And what is the issue here? There is some subtlety, because so in topology, if you get simply connectedness, so if you have path connectedness of these two base, in the space of two base paths, so automatically you get the path connectedness of the M-based space of M-based paths. Okay, so you can just increase the number of marked points. Okay, this is automatic, like in topology, but this is not the case in this setting. So you need to introduce a strong version of this rationally simply connectedness. So let me add it. And okay, so what is the difference? It means that you take any integer, okay, bigger or equal than 2, then there exists a d naught, which is of course depending on m, such that for every d bigger or equal than d naught, there exists, okay, here you just need to replace this guy by m dm, okay, and then of course here you're just replacing this guy by m, okay, so from m d m, okay. And then you ask the same. Okay, so you ask that this needs to be dominant and rationally connected. Okay, so you see this is it's complicated as a definition. I think I will. So maybe I will just think I commented enough. I think I will pass to examples. Okay, so to give you an idea of the problem of this notion, as you can imagine, just looking at the definition, is that it's pretty hard to get examples. Okay, so at least it's non-trivial to produce examples. So let me discuss some of them. So okay, so what is the first example? Of course, well, projective space, right? And this guy is strongly rationally simply connected. Let me write it this way. Okay, rationally simply connected and strongly rationally simply connected. And this is easy. Okay, this is maybe the only case where it's easy. Why? Okay, this I can do. I mean, you take degree n, degree d. Sorry, no, degree d morphism. This is just defined by P naught Pn, okay, degree D polynomial. Then you fix m equal to d plus 1 point in the projective space. And you fix same distinct point P1. And then if you look at the space in the morphism of degree D from P1 to Pn, such for the morphism which verifies that f of xi is yi for all I, and this is rational. Is rational. Okay, it's very easy to see, and once you have that, basically you have the rationally connectedness of all the space, all the modular spaces you want. Okay. Okay, the more complicated example, but still you can do it by hand. Okay. Is so take n bigger or equal than 3 and take the quadratic in Pn. So sorry, Pn in Pn plus 1. Okay, quadratic surface. And this guy is rationally simply connected. Is strongly rationally simply connected. You can do it by hand also. This is of course more complicated. There is a little more, so the linear algebra is more complicated, but still you can do it by hand. The third example is this is by the Jong, He, and Starr in 08. This very famous paper. So rational homogeneous varieties are rationally simply connected. So rationally simply connected. Let me put in parentheses strongly, like so this is my limit about understanding if you actually get the strong version of it. You certainly get a rationally simply connectedness. And this is also related to a very famous conjecture, which is
sorry, Andrea, I think we have a question. Someone raised a hand.
Sure, please.
Hello, can you hear me?
Sure.
Yeah, just curiosity, is there a positive characteristic version of this definition?
So certainly there is, but I mean, yeah, it's already quite complicated to check anything in over the complex numbers. But yes, you can just write a definition. You can do it. There is this paper by Chen-Yang Xu and Jason Starr and Chen-Yang Xu who get some results in positive characteristic.
Okay, but it's not just like taking the definition above and like probably adding smooth at the generic point is more complex than that.
Absolutely. You need to be much more careful.
Okay, yes. Perfect. Thank you.
You're welcome. Thanks a lot. Feel free to interrupt. Like this is I'm very happy to make it interactive. Okay. Okay. So the other example I want to make is, and this is to the Jong and Starr. So I mean, here are theorems, okay? Like up to example B, it's say it's maybe a long exercise, but like here are like very deep theorems. So this is a paper by de Jong and Starr, which is unpublished, and then there is a paper by Deland, which is student, I think, of de Jong or of Starr. Anyway, I'm not sure, but this is published. And let me, so this is the case of hypersurfaces of complete intersection, actually. So take n bigger or equal than 3, and take x dn, which is in Pn, general complete intersection of degree d, d1, dc. Okay, n is the dimension of the complete intersection, and then you get what you would hope for. Of course, is that if you take this complete intersection, this guy is strongly rationally simply connected, if and only if the sum of the squares of the degree is less or equal than n, or big N, sorry. Okay. Okay. Let me once again stress that this is exactly, or if you want, I mean, you can just retranslate this to Fano. So in this case, you really get the same thing, the same guy. Okay. Which is good. Okay. So it means that this is like the right notion. Okay. And so these are there are other examples for Grassmannian, for like sections of Grassmannians by other students of Starr, I think. But anyway, so my point is that there are these kind of examples for, but not like many explicit examples. Okay, so I don't know how much you feel satisfied with example. I was not, so I thought, okay, let's have a look at, and this is like third part, Fano threefolds. So maybe I should say smooth Fano threefolds just to okay, smooth. Okay. All right. So, and this is like the part we got some results, but this is still in progress. Okay. Let me. Okay, this is like a good moment to make some kind of a break, because this is I tell you what happened to me. So this Tuesday I was attending Vanya's talk about his very cool Fano project, and he was mentioning, the list of Fano threefolds, smooth Fano threefolds, the classification. And I was there, listening to him, and I started like thinking, oh yes, of course here I will focus on Picard rank 1, okay, definition I gave. And I realized, okay, so how many of them? So you get 17 families, right? Picard rank 1. Then of course there are 2 which are easy, which are just P3 and the quadric in P4, which are strongly rationally simply connected. So what is left is 15. Okay, and at some point I got a little like stuck because I got scared. I got a lot of anxiety because I thought, well, I'm not a religious person, okay, but I grew up in Rome, and the 15 I thought that is the number of station of the way to the cross. Like we're approaching Easter, Friday's Easter, so I thought, whoa, that's not a good sign. We are in the middle of this. We are kind of, going through the list, checking this rationally simply connected. I thought, whoa, this is not like a good sign. I got a little scared. So, well, whatever. And then I thought, no, but this is just superstition. And of course, anyway, the fact that I'm 33 didn't make me feel better. So anyway, I will try to be optimistic though, and present you what we get so far. And I want to start with a theorem which is not on rationally simply connectedness, which is by Araujo and Castravet. So take X as smooth Fano threefold. And you can check. So in this paper, it's a very nice paper. They check this two Fano condition on smooth Fano threefolds, and they get that X is two Fano. So this numerical condition on the second term character, if and only if X is P3 or the quadric in P4. Okay, but not much. All right. So here, so you see, this is a very strong condition. So the question we started with was to look at the next guy in the list, which is, so the next guy in the list is this Fano threefold, which is very famous, and it's great that Vanya mentioned it during his talk. I mean, many other people like also mentioned this, like in P6. Okay, this quintic in P6. Right. So this is, let me recall, like Vanya did, but let me recall, like, what about this guy? So this is just obtained as take the Grossmanian to 5 in P9, and you intersect the three hyperplanes. Okay, this is in P9. Okay, this the Picard rank of V5 is 1, and okay, you take the pick of V5, and this is just generated by H, and the canonical V5 just minus 2H. So the Fano index is 2. Okay, and V5 is rational, is rigid and rational. And you know, you have this explicit nice map which was described by Vanya, like you project from a line. I will recall this just in a second. And V5 is also quasi-homogeneous. Okay, so basically it's very close to all the classes where you have general results of rationally simply connected, but you don't. Okay, you cannot apply general results. And here's our main result here. Is that V5 is strongly rationally simply connected. Okay. Right. So you see, this is also showing you that the two Fano condition is not enough to get rationally simply connectedness if you are not in hypersurfaces. Okay. Okay. So let me sketch the idea of proof. Okay. So idea of proof. So take this M here D. Let me call this guy inside M 0 0 bar X D. So X is V5, of course. So this guy is parametrizing homomorphisms, as I said, which are birational onto the image, birational onto the image. Okay. The remark is that this guy is irreducible. Okay. this gets irreducible. Okay, so from our proof, this is a consequence of the proof. I remember discussing this with Cinzia, actually, okay, with Cinzia Casagrande, and she mentioned this work by Lehmann Tanimoto, so where they prove irreducibility of this guy. Okay, let me mention see also Lehmann Tanimoto in 2018. Where they actually prove reducibility, okay? But anyway, we don't need, so basically in the proof, we didn't really need this, but we prove it actually, okay, but anyway. So we need to prove that MD beer bar is rationally connected. Okay, so and that's where birational geometry, explicit birational geometry comes in. So take a general line L in V5, and then you look at the projection. So what Vanya described last time. So you okay, let me just, last one was on Tuesday, yes. So you get the projection. So take a general line, project from L. Okay. You end up in P in the quadrant P4. Okay, it's birational. And so the picture, let me make a little picture of this. So you have your line here, this is L. Then you can look at the divisor of lines through L. Okay, let me make it like this. Okay, it's not very precise. It won't be very precise. Those are the L, lines through L. And this is when you blow up the line and you contract this D, you end up, so the image is just this twisted cubic. So phi L of L, yeah, say C, maybe CL twisted cubic. All right, and so now, so the idea is basically to compare the rational curves in V5. This is V5, by the way. I missed the 5. This is V5. So take a degree D rational curve. Okay, so you get something like this. This is C. So C degree D rational curve. Right. So when you look at, you just send it in Q3, so you get something like this curve meeting, so phi L of C. Okay, this is gonna meet the twisted cubic. So what I'm saying basically is that phi L induces a map birational onto the image. Let me call it big phi, okay? So from MD bar to M00 bar QD, okay? So the issue, what I want to say is that what we need to prove, that the image is rationally connected. And so this is the idea. And so you see, and the strategy we have is basically to look explicitly at rational curves, so moduli spaces of rational curves in the quadric here in dimension 3. Okay, so that's why, in a sense, we needed. So I mentioned that you can really do it by hand. So looking at moduli spaces of rational curves on the quadric hypersurfaces. And here's what you need, because of course this is not like general fibers, okay? Those are like special moduli spaces, okay? So they're not like, so you really need to work out like details and check that these moduli spaces you get in the image are actually rationally connected. Actually, we prove something strong. We prove unirationality in this case. Okay. All right. So this is the idea. Let me also say, so what about the others? Okay, let me finish up with some final remarks. So final remarks. Okay. So the first one is about the strong version. So to prove, that was kind of a lot of work, okay? To prove the strong version of rationally simply connected for V5, we need to produce a twisting surface. In V5. Okay, I didn't say much about this, but maybe I can say it now. One of the strategy, this is really like, so let me say inspired, this is really like inspired by the strategy of the Jong and Starr and the land. So there is this notion of very twisting surfaces inside your Fano varieties, which is, in a sense, is the two-dimensional analog of a very free curve okay, which is, I mean, it's equivalent to rationally connectedness. So the thing is, it's basically a ruled surface inside your variety, which has like very kind of positive normal bundle. The thing is that it's pretty hard to produce those surfaces, and even more so, the strategy by the Jong and Starr and the land is to produce this scroll. They produce really a scroll in the hypersurface, in the complete intersection case, which is a very twisting scroll. The problem is that there are no very twisting scrolls in V5. Okay, so we need to pass to surfaces, I mean, fibered in conics. Okay, and for conics you can get singular fiber. So say computations get more complicated and involved in this case, but we managed to produce a twisting surface which is fibered in conics. Okay, so this is the idea how to do this. Second remark, which is, of course, what about the other Fano? What the other smooth Fano threefolds. Okay, and let me say we start of index 2, for instance, for Fano index 2. Okay, for this, those are, so all the others are not rationally simply connected. Okay, so we can show this, and the reason, so basically, if you want, you can really have a feeling about this, that something is wrong and something, so there are some kind of obstruction to be rationally simply connected, just looking at the space of lines on those Fano threefolds, so on the other Fano threefolds, which are not rational, not rationally connected. Okay, so what happens is basically that what you have to look at is to the induced morphism from those moduli spaces of rational curves to the intermediate Jacobian, and so basically all these morphisms are non-trivial. Okay, so this is how you show this. And what is the, so but in a sense, I mean, to do this, we really need to use the explicit classification of index 2 smooth Fano threefolds. So, and let me mention the part which is really in progress. And this really is from Laurent Gruson's ideas. So what we expect, so let me say what we expect. We expect that if, so H1, 2 is non-zero, okay, for the Fano, then X cannot be rationally simply connected, okay? And so, okay, so we really expect this. So there is one guy left. So one guy is left. So there is, and this guy is V22, okay, the famous Fano threefold. And about this, like, I really don't know. I mean, is rationally simply connected? I don't know. So, and you see, this is the 15 in a sense. And well, okay, so this looks hard. Okay, we cannot do it like explicitly with like explicit birational geometry methods. And you know, but about just to close with this parallel with the way to the cross, I thought, well, this is the 15th, it's going to be very, very hard. But then I realized that the 15th station is like resurrection. So hopefully, I mean, I feel confident that we can attack this problem. And also there is a good sign that the next talk is by Jesus. So it's like, I mean, good signs about this. And closely, I just close with this, and I thank you for your attention.